Okay, today is March the 16th. Happy Wednesday. Today we covered density. This is our first of two topics, two consecutive classes on physics applications. Density today and work next class. It's okay if you've never taken physics before, but if you have taken some physics already, then hopefully this will kind of connect to some of these formulas that you just used, or maybe you typed integrals into Mathematica. This will make sense of that. In terms of outstanding stuff, Project 5 is still on your plate. It is not due until our next class. Because of spring break, our next class is not until Monday, March the 28th. We have this coming Friday off, and we have all of next week off. So the next time we see each other will be Monday, March 28th, at which point you will hand me Project 5, at which point Project 6 will be officially assigned. But because there's this long gap, and you have all the tools that you need to do Project 6 now, if you wanted, I wanted to hand you Project 6 ahead of time. So not officially assigned, but if you want to look at it over break, you might come back and have it done before it's actually assigned. Okay, so I think that's it. Other than that, the next thing on the horizon is our test, April the 6th. Questions on the calendar? Okay, so again, we're on the top of page 53. Just a couple of other quick announcements. Number one, is anybody missing a graphing calculator? Because one was found in the Math Studio last class. If you are missing, was it covered in stickers? It was. It was found in the Math Studio by the computers on Monday. Chris, you can tell me what yours looks like, and I'll tell you if maybe we have it. Anybody else think maybe it's theirs? Okay. We got that. We got that. Speaking of break, I wanted to let you know that there is a resource available to you next week that you might not be aware of, and that's the peer tutoring program. They're available all week next week by appointment, and I expect it is a very underutilized resource over spring break. So if you're around and you want to get some either caught up or ahead in this class or maybe some other class, that would be a great thing to take advantage of. They're not open this coming Friday or Saturday, but they're open every day next week. Okay, good there, got that. And then finally, if you came in a little bit late, your classmates will show you two typos that we fixed right before we officially started today. And one other thing I want to mention, if you do your homework assignments from the syllabus, right, like in the syllabus it has the page, the chapters and the problems you're going to do, the homework for this class right here that we're about to do is wrong in the syllabus. So do the assignment that's in the packet itself. Right after each lesson, you find the homework assignment. That one is correct, but the one in the packet is not quite right. Okay. Yes. Space after. Oh, thank you. Thank you. Thank you. No, the packet is right and the syllabus is wrong. All right. So I think we're good. All right, so let's jump in here at the top. Daily summary. Today we use calculus and the methods of slicing that we've been developing to calculate mass. Here we go. Number one, find the mass of a cube with side length 3 inches and a density of 2 pounds per cubic inch. It strikes me as being a quite dense object, but let's see if we can find the mass of this cube. So I guess we should find the volume, right? So what's the volume of that cube? Is 3 times 3 times 3, right? 27 what? Cubic inches. And we're trying to somehow use the density. It's a 27 cubic inch thing, but the density is 2 pounds per cubic inch. What am I doing with the 2 and 27 to find the mass? Multiply, right? And even if you're not sure about that calculation, at the very least, like this is a formula that appears down below, but at the very least, you should buy that multiplying these two guys has the benefit of getting rid of the, or making the units do what I hoped they would do, right? 2 pounds per cubic inch, right? In that order, the cubic inches cancel, and I get 2 pounds, which I guess technically is not a mass, but rather is a weight. But I'm not smart enough in physics to know the distinction, so I'll use mass, but sometimes I guess I'm talking about the force that is weight. Yeah, Dave. Yeah. Yeah. Okay, so we get 54 what here? Pounds. 54 pounds. Fair enough? So we're buying that the mass, or weight in this case, is volume times density. That's reasonable, right? Okay, so the difficulty is going to come up when the object that we are trying to find the mass of, like this cube, doesn't have a uniform density, but rather maybe the cube has a higher density at the top than at the bottom. And so finding its mass is going to be quite a bit more tricky than just doing volume times density, because that density is changing. Here's our three formulas for mass. If you're in the 3D case, which we just were, then we see that mass is volume times density. That's what we just used. If you're in a one-dimension case, then volume, I guess, is just a distance, right? And if you're in a two-dimension case, then volume maybe is an area. But in any event, you multiply one of those things by the density, and it gives you the mass of the object. So what we're going to do is, let's just jump to 4, and then we'll talk about 3. An open cylindrical barrel of diameter 7 feet and height 21 feet is filled to a depth of 10 feet by muddy water. The density of the water varies. The water at the top is probably not as dense as the mucky stuff at the bottom, right? So we've got some specific data in here which we'll use, but don't get lost in the details. It says, well, the density we'll assume varies linearly throughout the bucket as a function of the depth of the water. At the top, the density is 80. At the bottom, it's 30. That's fine. We're going to find the total weight of this muddy water. So let's see if we can draw a picture. So we've got our cylindrical barrel. We'll mark some dimensions here. It says the diameter is 7. Diameter is not the most useful thing to know about the circle. Most of our formulas have radius in it, right? So I'm just going to right away translate this to a 3.5 inch radius. Is that fair? 3.5 foot radius, thank you. 3.5 foot radius. The height is 21, but the thing is not filled up, so I'm going to put the water line here at 10 feet from the bottom. And we want to find the weight of all of this muddy water. But it's complicated, right? Because a scoop of water at the top does not have the same weight as a scoop of water at the bottom, because it's very muddy at the bottom. Yeah? So here's what we have to do. We have to grab these scoops of water in such a way that all of the water molecules that are in our scoop have roughly the same density. So a vertical scoop. Weird is okay. All right, so Yanni is suggesting that we slice it this way, right? Just like grab a slab of water that way. Is it true that the water molecules in that slab have essentially the same density as each other? The answer is no, because the stuff at the top is very different from the stuff at the bottom. But I like the idea of grabbing a weird slab. So what would be a slab where the density is roughly constant is a horizontal slab. So we're going to slab right through the middle. Let me try that again. So we're going to slab right through the middle. Right through the middle. I want to draw 2 of these. Why can't I figure out how to draw 2? I want to give it a tiny bit of thickness, but I don't want to muddy up my picture. All right, how about that? Is that all right? Just the bottom guy? Okay. All right, so we've got our slab, our circular slab of water. Yeah, it's hard to grab that slab with a cup, but we can agree that the water molecules in that slab have essentially the same density as each other. And I've drawn that slab with quite a bit of thickness just so we could see it. But if you made a razor thin slab, then pretty much all the molecules in the slab can be treated equally, right? So grabbing stuff that has the same density because it's all the same distance from the bottom. Okay, so on the slab, I think I'm ready to find its weight, I guess. Weight of one slab equals. So we're using our formula from up above. This is the 3D one, so it's volume times density. The name of that green slab is what mathematical word? The name of that green slab. Disk is okay. Slice is okay. Circle is the 2D version. It's a cylinder, right? So it's a really stubby cylinder. So I need the volume of a cylinder. What's the formula for the volume of a cylinder? Pi r squared h, that's good. Multiplied by the density. Now the book uses one of two letters. We'll use them kind of interchangeably. What Greek letter is this? That's a lowercase delta. It's Greek D. Okay, so we've got volume times density, and now we're going to start filling these things in. So pi times, all right, the radius of that green slab is how much? 3.5. If I slide that slab up and down, does the radius change or stay? Stays, so I'm safe putting it as always 3.5. It doesn't change. The height of that slab, I haven't symbolized yet, but what do you think is a good symbol? Like a delta H. Yeah, so let's start putting some letters in here. So, how are we differentiating this sigma or this delta? I mean, this is a capital delta. Lowercase stands for density. Yeah, it's just a symbol for density. Okay, so delta H, that seems good for the height or the thickness of my slab. And now I'm going to multiply by the density. Now I'm going to put some blank parentheses here. I got to find a formula to put in there. And is the density constant or changing as that slab moves up and down? Changes. So there's going to be kind of a complicated formula that's going in the parentheses here. So we need its formula. It's pretty clear that the density of that green slab depends on how far you are from the bottom, right? Because that's the given information. So it's really mucky and dense at the bottom and kind of clearer and less dense at the top. So I need a variable to tell me how far I am from the bottom. So H. Okay, so let's see if we can come up with a formula here. I know that if I write ordered pairs for height and corresponding density, let's see if we can translate this information into two ordered pairs. Thank you. Okay, the first thing, it says the density at the bottom is 80. What is H? 0 at the bottom, and the corresponding density there is 80. And then the other sentence said at the top, it's 30. Yeah, well, I thought it was a 20. Is it 21? Yeah, it's only filled 10. There's no water up there. So I think the assumption here is that we're talking about at the top of the sludge is a density of 30. So we've got our two ordered pairs. And the key phrase in the problem said assume that the density varies linearly with the depth. So this is a problem of finding an mx plus b, right? We got to find the equation of the line that connects those two things. So we're not gonna do the work, but I trust that we all have the ability to find a formula there. So let's just write the answer here. Delta equals, I think it's a negative 5h plus 80. So a little bit of work involved there, but we all know y equals mx plus b calculations. So that is our density formula. Again, changes depending on how high you are from the bottom. And that formula goes right here in the parentheses, negative 5h plus 80. So that is the weight of one slab. Fair? And I wanted to find the weight of all of the water. So what's the next thing we're going to do? One in-between step and then the integral. So if we want the weight of all the slabs, then we're just going to add up all the, all the things that we just came up with. So sum of all of this stuff. Yeah. I'll talk about it. Okay. So I'm being really lazy here by pointing arrows. I'm also being lazy not putting like a subscript of I, right? Technically, we're counting our slabs. I guess probably that negative 5h should become a negative 5h sub I, and then let I go from 1 to n. Totally okay for you to be the same lazy as me here. And then the actual weight of the whole thing, okay, if we just let the thickness get really small and we do more and more slabs, then that summation becomes an integral. And so again, I mentioned that a lot of these problems in the next few weeks just turn into integrals, but I don't want it to be magic. I want it to be reasonable. Why an integral is the right thing to do. Whereas, our formula, volume times density, there's nothing in there that says integral. But it's this idea of slicing so that you can largely treat all the water molecules as constant, turn it into an integral. Yeah. Times h for what? No, just adding them all up is throwing this whole big thing into a summation. And we put our kind of optional sub I. That takes care of counting them and differentiating them from each other. Okay, so let's throw it into an integral here. What do we get? Pi 3.5 squared. Delta H becomes dH. That's fine. Everything else just gets copied. So this translation is really easy. Setting it up is like getting that calculation up above. That's the heart of this problem. Pi 3.5 squared can come right outside. We do need limits on our integral. This is where you do have to think about your picture. Take that green slab and move it up and down. 0 to 10 is good. Okay, so this integral is not very hard. This is just integrating a linear thing. We're not going to do it right now. We're not even going to type it into the calculator. I'm just going to, don't do this on the test, but that's it's easy to do, right? But don't do that on the test. Okay, so Dan asked a very good question. Like what do we really need to show in terms of the test? Can we just jump to that integral? Do we need the summation? Do we need a diagram? What do we need? So I will be very clear. Here's what you need. Before I see an integral, I need to see two things. I need to see a picture that is well labeled, and I need to see this calculation right here for the mass or the weight of one slab. I don't need to see the summation, but I got to see those two things, a well-labeled diagram and the calculation for one particular thing. If you just jump to an integral, number one, there's a decent chance you're not going to get the thing right, but number two, it's not illustrating why the integral is the right tool. Because like I said, nothing up here suggested integral until we got to this idea of adding up a bunch of representative weights of slices. Yeah. Okay, and I say well labeled, because we put H here. This red thing was the H that we decided, but couldn't you just as well let H be how far it is from the top of the water? The calculation would look different. You'd end up with the same final answer, but the integral would be different. But it's legit. Couldn't we also have let H be the distance from the top of the barrel to the slab? Absolutely. You'll get calculations that look different, but at the end of the day, it's the same volume number you'll get or same weight at the end. So I need a well-labeled diagram. This isn't just me saying good practices. This is me saying I need to understand what your variable represents so I can judge whether or not the expression is correct. So make sure you're clear on your labels. Okay, I think that is good. The activities start on the next page. Just to be clear, here are the directions. Oh, yeah, 3 we just kind of, 3 essentially just says slice the thing so that we have uniform density and then add up the slices and then it's an integral. Yeah. Okay, I think that is good. So on the next page are the activities. Just to be clear, here are the directions. Let's look at them all together. You are going to set up the integral, and that is all. You're not going to actually do the final calculation until you set up all of the integrals. If you have time at the end, you'll do all the integrals. But all you're doing is typing these guys into the calculator in the first pass through. Okay? Diagram, weight of rep 1 slice, then the integral. 3 pieces. All right, go ahead. I'll walk around.